Okay, Assalamualaikum and good afternoon to all. My name is Najiyah SAFWA binti KHASHI'IE, and for today, I will present and share half of my research findings entitled Meets Convective Stagnation Point Flow of a Thermally Stratified Hybrid Copper Alumina Water Nanofluid over a permeable stretching or shrinking sheet in the INSPAM Postgraduate Dialogue and Annual Awards 2020. So thank you to INSPAM for inviting me to share my research findings in these 3 years of my study. Okay, so actually this research finding has been selected, has been presented and selected in ASM Science Journal during ICOIMS 2019. So ICOIMS stands for International Conference of Applied and Industrial Mathematics and Statistics, which is organized by Faculty of Science and Technology Industry, FIS UMP Pahang, okay, in 2019. Okay, so this paper has been published in ASM Science Journal. Okay, so this is me, okay, Najiyah, and this is my supervisor, Prof. Dr. Norihan. Okay, and between us is Emeritus Professor Dr. Ayan Pop, okay, which has been my co-authors of most of my papers. Okay, so this is the outline of the presentation today. Okay, hybrid nanofluid. So actually my research is mostly about the boundary layer flow of nanofluid and hybrid nanofluid. Okay, hybrid nanofluid is a new kind of nanofluids which is prepared by suspending different types of nanoparticles in a base fluid or hybrid composite nanoparticles in a base fluid. Okay, this is from Saka et al. In 2015. Okay, so but for my case, for my study, so I'm doing a numerical investigation or numerical study, okay, for hybrid nanofluid model. Okay, so in real, so hybrid nanofluid ni can be prepared by suspending 2 or 3 types, 2 or more types of nanoparticles in a base fluid. Okay, or the nanoparticles itself is in hybrid form. Okay, and then dispersed in the base fluid. Okay, may offer a good thermal characteristic as compared to the base fluid and nanofluid. Okay, so and single nanofluid lah as a result of synergistic effects. So this is from review paper, which is written by Siddiq et al. In 2016. Okay, so this is a few of base fluids, okay, based on the review paper by Sajid and Ali in 2018. Okay, so the base fluid can be either water, ethylene glycol, water and ethylene glycol mixture, vegetable oil. Okay, so there is a few types of vegetable oil. Okay, but in my study, in my work, numerical works, okay, mostly I'm analyzed for the base fluid water, for water-based fluid. Okay, while this is a few class of nanoparticles, so actually nanoparticles can be divided into 5 major nanoparticles group lah, 5 major group, which is metals, metal oxides, carbon materials, metal carbide, and metal nitride. Okay, so from metals, we have copper, silver, nickel, okay, metal oxides, alumina, copper oxide, iron oxide. Okay, carbon materials have carbon nanotubes, okay, CNTs, okay, and then we have multi-wall CNTs or MW CNTs and graphite. Okay, so this is a few types of nanoparticles, okay, and for the hybrid nanoparticles, so we choose 2 or more nanoparticles. So for in my numerical work, so I'm I'm use, okay, the model with copper and alumina. Okay, so from metal and metal oxides. Okay, so to analyze the boundary layer equation of hybrid nanofluids, the model itself has thermophysical properties or correlations, okay, to analyze the boundary layer equation for hybrid nanofluid. Okay, so in this work by Devi and Devi in 2016, so they propose a special form of thermophysical properties, okay, for the hybrid nanofluid. Okay, so in this table there are two set of thermophysical properties, okay, which is the first set ni for nanofluid, for single or mono nanofluid, okay, and this second set ni for hybrid nanofluid. Okay, so this is the thermophysical properties for density, heat capacity, viscosity, thermal conductivity, and electrical conductivity. Okay, since we do not conduct any experimental work, okay, so we use these thermophysical properties, okay, to compute, okay, the approximate density, okay, density for the hybrid nanoparticles. Okay, for example, density, heat capacity, okay, viscosity. Okay, so that's why we have to choose the thermophysical correlation. So in my work, I use the thermophysical properties from Devi and Devi. Okay. Okay, so stagnation point flow. So stagnation point flow, fluid flow that approach a solid surface and then separated into different streams. Okay, stagnation region has maximum pressure, heat transfer, and mass disposition. Okay, so this is a stagnation point flow. Okay, here. Okay, so this is a stagnation point flow. Okay, into a vertical. So this is a vertical flat plate. Okay, so this is few literature that focus on stagnation point flow, which is originated by Hymans in 1911. Okay, so this is only a list of literature that study the viscose and hybrid nanofluid flow for the stagnation point flow. Okay, so start with Chiam in 1994 for stretching sheet, okay, and then Wang for shrinking sheet, okay, and then for hybrid nanofluid, we have literature from Nadim et al., Rostami et al., and Dinarvan et al. And for the present work, for the present sharing ni, okay, I focus on stretching and shrinking sheet, okay, means that the plate, okay, the plate is not it is a flat plate, okay, but there is a stretching and shrinking velocity that works on that plate. Okay, and then we have mixed convective flow with thermal stratification and also do the stability analysis. Okay, so inspired by Rostami et al. In 2018, the objectives are to identify all the possible solutions in the governing problem and conduct the stability analysis. Okay, identify all the possible solution means that, okay, for the boundary layer equation itself, so the solution may be one solution, okay, maybe unit solution or one solution, or the solution can be dual, or there are two solutions or multiple solutions. So that's why, okay, we use stability analysis, okay, to check, okay, which one of the solutions, okay, if there is more than one solution, okay, which one is stable, which one is the physical solution or not. So that's why usually, okay, for the boundary layer problem, okay, with two solutions or more solutions, okay, so usually we have stability analysis part. Okay, and then study the impact of the parameters, okay, copper nanoparticles, suction on the skin, friction coefficient, and heat transfer rate. Okay, so this is the difference between the present work and Rostami et al. Okay, and this is the methodology of this work. Okay, first we have boundary layer and energy equations in PDE form. So PDE, partial differential equation. So due to the complicated form, so this boundary layer and energy equations have to be reduced to nonlinear ODE, okay, using similarity transformation. Okay, and then we solve it using BVP4C function in the MATLAB software. So the researcher also can use another methods, okay, such as shooting methods, okay, Runge-Ketta methods, or there are also researchers that use analytical solution, okay, to find the solutions for the boundary layer problems. Okay, for the appearance of two solutions or multiple solutions, so the stability analysis mostly conducted, okay, to check the physical or real solution. Okay, so this is the physical model. Okay, so where for this problem, a stagnation point flow of hybrid copper alumina nanofluid towards a stretching or shrinking sheet is considered. Okay, the sheet is permeable to allow the fluid suction process. Okay, the stretching or shrinking sheet, okay, means that this flat plate, okay, so it's moved with a linear velocity UWX equal to AX. Okay, so this is a linear velocity, okay, for this flat plate. Okay, and then the free stream velocity, so this is the outer flow, okay, is UEX equal to BX, where B greater than 0. Okay, so here we have stagnation point flow, okay, with velocity UEX equal to BX. Okay, so usually the stagnation point flow, or we call it free stream flow lah. Okay, thermal buoyancy force is considered to deal with the thermal stratification effect. Okay, so this is based on the study by Mak Yassin et al. In 2013, Bestapu et al. In 2017, and Anima Saun et al. In 2019. Okay, so what is the stratification process? Okay, usually researchers always assume that the temperature can temperature in a constant form. Okay, so wall temperature constant and the ambient temperature or far field temperature is a constant. Okay, but for the stratification process, okay, both of the temperatures, which is wall temperature and ambient temperature, is in the variable form. Okay, means that dia ada dalam bentuk ni lah, variable. Okay, so the linear stratified ambient temperature T infinity X. Okay, T infinity ni stand for far field temperature equal to T0 plus AX per L. And then the variable wall temperature is T0 plus BX over L. So T0 ni is the initial ambient temperature. L is the characteristic line of the sheet. Okay, A greater than 0 and B is the characteristic temperature of the wall surface. Okay, so this is based on the, this assumption is based on this paper lah. Okay, so this is the governing model, okay, from PDE. So this is the PDE form. Okay, we have boundary layer equation. This one is continuity equation. So the first one is continuity. Okay, second one is the momentum equation in X direction. So this is a two-dimensional model. So we have X direction. Okay, so this is UE dUE per dx stands for the stagnation point flow. Okay, and this is the term for convection. Okay, the third equation stands for the energy equation, and this is the boundary equation. So due to the complexity of this form, PDE form, so we can't solve it directly. Okay, so we have to reduce it to the ODE form using appropriate similarity transformation. Okay, so this is the similarity transformation. Okay, and this is the thermophysical properties of hybrid nanofluid from Dewi and Dewi. Okay, so following Dewi and Dewi 2016, Okay, so first nanoparticle is alumina with 10% solid volume fraction. So Phi1 is set into 10% or 0.1. The solid volume fraction for copper is varied. Okay, the model is reduced to the viscous fluid when both Phi1 equal to Phi2 equal to 0. Okay, and here is the thermophysical properties of water, alumina, and copper. So these properties for the base fluid, okay, base fluid and the single nanoparticles. Okay, so these properties actually we can obtain it, okay, by other literatures or also in the textbook. Okay, so while the properties for the hybrid nanoparticles, we have to use this correlation. Okay, so that's why there are many types of correlations for hybrid nanofluid. Okay, but for this work, we use hybrid nanofluid correlation of hybrid nanofluid from Dewi and Devi. Okay, so this is the stability analysis formulation. Okay, and then this is the physical interest of the study, which is skin friction coefficient and local Nusselt number. Okay, so skin friction coefficient to measure the fluid flow characteristic. Okay, why the reduced local Nusselt number? To measure the heat transfer process. Okay, validation of method. So the comparison results between present BWP4C method is conducted by, between Rostami et al. And Ishaq et al. Okay, with the present work, and we can see that all of the data are in a good agreement. Okay, so this is the first solution. This is the second solution. So we compare for the case of viscous fluid. Okay, so this is the results that are obtained using the BWP4C solver. Okay, so the application of suction is necessary to induce both first and second solutions. Okay, both CFX, okay, and NUX, skin friction and heat transfer rate for first solution incline with the increment of V2. Okay, hybrid nanofluid with copper fraction 0.05 has higher heat transfer rate as compared to the copper water nanofluid and viscous fluid when S ni equal to suction parameter equal to 0.5 for both stretching and shrinking case. However, an astonishing result, okay, opposite result is obtained when higher S is applied. So S has effect, okay, for the results of heat transfer. Okay, dual solutions are attainable for both existing and opposing flow. No second solution for forced convective flow. Okay, so existing flow ni when the value of lambda greater than 0. So that is the existing flow. Okay, opposing flow, lambda less than 0. And at lambda equal to 0, no second solution. So that's why there is a dot here. Okay, means that the value here is undefined. Okay, and this is the result for the smallest eigenvalue. So the first and second solutions have positive and negative smallest eigenvalue respectively. Okay, which implies that the first solution is physically stable when the value is positive. Okay, so this is the conclusion. So from this study, it can provide idea to the researchers on how to increase or decrease the heat transfer rate by controlling the parameters such as suction. Okay, so as we obtained just now that when suction is increasing, okay, or if the value of suction is high, okay, so the heat transfer rate reduce, okay, when Phi2 when the copper volumetric concentration increase. Okay, but if suction is small value, okay, 0.5, so the heat transfer rate is increasing, okay, as the copper volumetric concentration increase. Okay, so this study give idea to other researchers. Okay, so actually suction have own effect lah to the value of heat transfer rate. Okay, so for the acknowledgement, I want to thanks to the University Putra Malaysia, okay, for the grant, okay, for the financial support, and also to the INSPAM, okay, to the my supervisor for all the financial support lah through the grant. Okay, so thank you very much.